So, I think everybody here understands Hebrew. Maybe some of our viewers abroad. Okay. First, question. Does any one of you take any exams in the coming 2 weeks? You do. I was about to suggest that maybe we'll continue the course for the next 2 weeks. But okay. So I don't know. If all of you would like to continue studying next week and the week after that, then fine. And if not, also fine. Just let me know. And now, well, I've seen worse, but not much. זה מוחק יותר טוב, לא? אולי קצת, נראה. נמשיך אחר כך. אוקיי. So, let's see. So, what we are doing now is examining the quantum interaction of a general electromagnetic field with a two-level system. The electromagnetic field is purely classical, well, what we did was to look generally at the Schrödinger equation. So we were saying something like, look, we have a Hamiltonian. The Hamiltonian is, well, we just write it as ground state energy, which we assume to be 0. That's h bar omega atom, which we assume to be, well, that's the energy of the atom. And then we had oh no, that was just I would write it first as d dot e of t. And we said, and the state psi was just simply, I don't know, C ground, C excited, and we wrote and the point is that this is a time dependent. I'm reminding you quickly of what we did last time. So, well, then we had two things. One was that the field is something like, well, I don't know, it has some E0 times cosine omega laser t, and therefore we can write it as E0 over 2 times e to the I omega laser t plus e to the minus I omega laser t. And if it has a phase here, if there could be a phase here, then this phase will come here and will be here minus phi And then what we did was to say, okay, I can write, so we can write equations for C ground dot and for C excited dot. We did that equals, for example, in this case, this one, the C ground dot would be just simply D dot E0. So here we'll have IH bar D dot E0 times C excited. And we called, so we took this one divided by H bar and called this entire thing the Rabi frequency, omega, actually omega naught, omega 0. General Rabi frequency could be something else, and we did the same here. And then we said, let's move to the rotating frame, so that moving to the rotating frame meant that, so let's write something like C excited equals B excited times e to the minus I omega laser t. There's nothing in that, and C ground, we said, okay, that will be still B ground. So we're moving from C to B. Why are we doing this? Well, because first, omega laser and omega atom are close. Now, and another thing that I assume is that this Rabi, this term, is small relative to this one. The atomic energies are bigger than the coupling. This is a coupling term. This is the external field. The atomic energy is much bigger than this because it's much smaller. Then I could say, look, this matrix, it's not diagonal, but it's close. These elements are much smaller than the diagonal. And therefore, it makes sense to assume a solution which is close to the solution that you would expect. So now, given all of what I just said, it would actually make sense to pick here the atomic frequency. And we can do that as well. We can solve this way as well. But as I told you, look, omega atom and omega laser, we assume that they're close. And we know that using the laser frequency actually makes things easier. Because if I choose the, okay, or let's put it like this. If I choose the atomic frequency, why would I do that? I would do that because I would expect that most of, because I know the solution without, I mean, if this doesn't exist, then I know for sure that CE equals just some initial value times e to the I omega atom t minus. So this is the solution that we know. So we're saying, look, I assume I want to see, B will tell me if B is constant, I'm exactly there, and if B has some slow dependence on time, then I'm not perfectly there. And actually, I strongly encourage you to do that. To see what happens if you rotate at the atomic frequency and not at the laser frequency. But rotation at the laser frequency basically has the same logic. And as we will see, it helps because the time-dependent part of the Hamiltonian rotates at the laser frequency and not at the atomic frequency. So if I rotate at the laser frequency, I have the option for the Hamiltonian to become time independent. And that's why we choose that. So that's for that reason, we don't go with the atomic frequency, we go with the laser frequency. And then, and by doing that, we can, of course, and then what we did was to say, look, CE dot equals BE dot plus minus I omega laser BE times e to the I omega laser T. And what is convenient, of course, and by doing that, we could, and then what we did was to put that here and identify that we have things on both sides that go away. For example, let's just look again only at the ground part here. So if I look at this equation here, and I'll remind you that we can look at CG dot, okay? So I'll write here, I'll replace that with BG. So that equation becomes just I BG dot equals what? Omega 0. And then here times e to the I omega laser T plus e to the minus I omega laser T. And then what? CE, but CE is this one, so we have here BE e to the minus I omega laser T. And now we can see that we have here, and that's convenient. So I have here two terms. And the reason I remind you this is because what we're doing now is we're going to throw away the counter-rotating term. Or what we have is omega 0 plus times 1 plus e to the I 2 omega laser T times BE. That's what IBG dot equals. And then we say, look, this is a derivative. This is rotating extremely fast in time, which means that whatever it contributes, it doesn't contribute for a long time. It very quickly becomes opposite. So we just throw it away. It averages out. It doesn't have, we assume that the dynamics is much slower than the optical cycle of the laser. Why we assume that? Well, we assume that because we know that the dynamics is induced by this term, and this term is by definition smaller. We assumed this. That was the assumption. So whatever dynamics it induces, it must be much slower than the dynamics that this one induces, or the laser frequency. So since we expect this dynamics to be very slow, we can throw this counter-rotating term. And that means that the field, and of course for when we write it here, then we end up with a different equation, and I'm not writing that, but again we throw away, here we will have e to the minus I omega twice, all right, 2 omega laser T, something like, yeah. And this is the term that we throw away. And again, we enjoy the same trick. So we did that, and we found that under the rotating, so that this, throwing those away, is the rotating wave approximation. And it's very common in everywhere, on linear optics, everywhere. It's a standard, really standard trick. Then we have a new Hamiltonian, which is in the rotating wave approximation, and because we threw away the counter-rotating term, this new Hamiltonian is time independent. Or I can say basically like something like I times BE dot BG dot equals now the rotating wave times. We have again a Schrödinger equation, but here we have and it looks like that. Omega 0 or omega 0 over 2. It always has to do with something. I think we'll have, yeah, we have a half here somewhere. So usually we write it like that. Now, let me remind you something. I told you that we could have a phase. The field could have a phase. What would that do? For example, so if I had, if that was not a cosine but a sine, okay, that was not a cosine but a sine, then this phase here would have been pi over 2. Right? I mean, it could have been like, I could take that as a phase of pi over 2, and that would mean that actually what happens is that this is a complex term. What actually happens here is that in general, I would have here, this would have a phase. So this, you know, okay, so as you know, I can write this E of t equals E0 times cosine omega laser t plus some kind of a phase. I could write that as the real part of E0, but now e to the I phi times e to the I omega laser t. Maybe minus, but I don't know, I'll put here a minus and then double minus. Or, in other words, I could call this the complex field, and then all that I would have here, and that means that basically this can be a complex term, but the Hamiltonian needs to be Hermitian. And all that happens is that this becomes complex conjugate. So generally, I can write, look, this omega naught can have is d times E0 times e to the I phi divided by h bar. It has a phase, the phase of the field. And you can follow the calculation assuming that, and you'll see that you get into the same thing. This is if the field has a phase. It is important to remember that, because something, okay, in the two-level system it's not important. Why? Because that's the only phase that there is, and an overall phase is something that you can always throw away. But if you have more than one field, for example, when we start thinking about, say, three-level system, when you have more than one field, you have two driving fields, or things like that, you can do similar tricks, and we will show something like that. But then the relative phase between them is important. Maybe one of them is a cosine, the other one is a sine, and it is important. It can be important. So, so then we need to remember that what actually happens is this. And what we did last time was to say, okay, so that is the rotating wave Hamiltonian, and within the rotating wave approximation, solving a two-level system interacting with a time-dependent field is nothing but solving a two-level system when interacting with a general Hamiltonian. But the general 2x2 Hamiltonian is not very hard to solve, and we can solve that, and we did that last time in two ways. Let me remind you the second way that we did, and that was to say, let's diagonalize the Hamiltonian. So we looked at the, what we did last time was one, solve in the bare atom basis. If I want to solve in the bare atom basis, means that I want to find B E of t and B ground of t, and we did that. We found that, we solved it, and we saw that we have a solution. The solution was basically showed that what you have in general are oscillations. If this is time and this is I don't know, like and assuming that initially the excited state, if this is, I don't know, like B E bariboa, and you can have, the solution is doing this. It is oscillating at a frequency of omega. Omega and omega 0 are related but not the same. Omega equals square root of omega 0 squared plus delta squared. The detuning delta is the detuning omega laser minus omega atom. Yep. And if I forgot a half or a quarter or something like that, forgive me. It's not the critical part. It's just a matter of no, I think it's okay. It's okay. And and also this amplitude, it depends on the detuning as well. So as far as I recall, this is absolute value of omega divided by omega 0 divided by omega squared. So now it depends, and we can see therefore that when we are on resonance, so when the detuning is 0, the laser is exactly at the atomic frequency. The solution tells us somebody's trying to trick me. All of those are black, but they're not. And this one is supposed to be red, but it's not. Okay. We'll try to return things to the way they should be. It's not me. And now we're left with one that doesn't have a hat. Okay. Well, let's do it like that. At least all the real black ones will be covered with a black hat. And there's one that, okay, never mind. So I was saying something like on resonance we have something like that, and then on resonance this is omega 0 and the magnitude is 1. So that's what we did last time, and we found that and then we were puzzled a little bit. We were puzzled by the fact that this solution has nothing to do with the rate equations that we solved a week before. Because the rate equations showed a convergence towards some kind of a steady state that could never be more than 50%. In a two-level system, you cannot. Even if you put the strongest field in, then it will never be 100% excitation. The maximum you can bring is to equality of populations. And here we have something like this. And I could also draw the ground state does the opposite. So that's for B ground, absolute value squared. And we have to solve this puzzle, and we started looking at reasons why, where this can come from. That's going to be the point of discussion for today. So that was just a quick reminder of that. But let me also remind you that the other thing that we did was to solve at the dressed basis, dressed atom basis. And this had to do with just diagonalizing the Hamiltonian. So this is just a 2 by 2 matrix. And we found new states. So we found the plus state, where H, rotating wave approximate. I always mean the rotating wave of P Hamiltonian, so I'm not going to write it. H plus equals lambda plus times the same state. H operating on state minus equals lambda minus on the same state, and we can find the eigenvalues, which are the eigenenergies of this Hamiltonian. Those are the dressed energies, and those are the dressed states. And what we did last time, in the end of our meeting, was to actually write them, to solve them. And we discovered let me just write the eigenenergies for us. We had here, I think those are right. So we had lambda plus minus equals, let's see. think that was the solution, and we also found that, and we looked at this in two cases. One was for on resonance. So on resonance, delta equals 0, and then lambda plus minus are just plus minus omega naught over 2. So that means, and we can also then find the two states, and we find that plus equals just 1 over square root of 2 ground plus excited, and minus 1 is so that means that on resonance, assuming the field is on the atomic resonance, the new states, the eigenstates of these Hamiltonians are not the ground or excited bare states of the atomic Hamiltonian, but actually a complete mix. And those two states have energies that are separated by the Rabi rate. So we have now, so if I look at this, I would say, look, I have two states. They're the minus state and the plus state, and they're separated by h bar omega naught. So those are the dressed states. And therefore it is no surprise that if I look at the ground or excited dynamics, I see this frequency there. Because the ground, I can say, look, the excited state is simply 1 over square root of 2, what? Plus minus this. Right? Yes. Yeah. So, therefore, the excited population, this one accumulates a phase with a plus omega 0 over 2, this one accumulates a phase with a minus omega 0 over 2, and therefore this one is oscillating like a sine wave at that frequency, no surprise. So that was one thing that we discovered. The other thing is that we also could look at what happens when we have a highly detuned field which is non-zero. The other thing that we did was to look at, okay, again, I'm looking at the eigen energies, but now away from resonance, meaning that the Rabi rate is much less than the detuning, but it's not zero. You cannot assume it to be zero. So under this assumption, I can take these eigenenergies and I can write, and I can find that under this assumption, or basically what I'm saying is that omega 0 divided by delta is much less than 1. So I can expand it using this parameter for expansion. And I think we did that last time, so let's remind ourselves what we get. We get here, so I have lambda plus and lambda minus. And let's start with lambda minus. This one becomes approximately omega 0 squared divided by 4 delta squared. No, 4 delta only. Of course. And this one becomes approximately the detuning minus so that means, so we can see a correction. When we assumed that there was completely no light on there, so here the light is non-resonant. It doesn't do much. If we look at the population, this excited population is nearly zero because, well, you could see here we have the detuning below, here we have the, this is a very small number. So if we look at population, almost nothing happens. The excited state remains pretty much empty. Population is in the ground, it remains there. There's a tiny fraction that appears on the excited state and oscillates very quickly, but it's very, very small. But still something happens, and that is the energies are shifted. What will, and how would we measure that? What do I mean? When we have at omega 0 equals 0, no field, and the energies are simply, the states are the ground state, which has an energy of 0, and the other one is an excited state, 0, and this one has an energy delta. Well, why not omega atom? Well, of course, we rotated away omega, so we're rotating at omega laser, so at the rotating frame, the excited state is delta away. And now what we see is that when omega 0 is non-zero, the states change. This one is shifting slightly up. This one is shifting slightly down. And they're shifting by the same amount, which is proportional to the intensity of the field. So this is d squared E0 squared, or let's just write it absolute value squared like that, because as I told you before, the field can even, omega 0 can actually even be complex. Divided by, yeah. No, only delta here. And delta, and I think that will be kept with maybe only one h bar. I don't remember. And maybe I'm missing an h bar, but forget about that. No, that's just the frequency. So h bar is here, and but those are for the frequencies. Never.
Delta is squared or not squared?
Not.
At the lambda plus, you write squared.
Of course, it, okay. So you can, you tell me. There's a very, very quick way to check, and this should be something that you're doing constantly. You should be screaming at me, this cannot be, because units are wrong. Okay? And therefore you know what it should be. Okay? Units should be those of frequency. So we should always check for dimension, physical dimension. So what we discovered is the light shift. So that means that those states, their energies are moving, and we can really measure this. Now, this shift is something that can be measured. Let me tell you how. We need now two lasers, okay? Let's assume that I have one laser that is off resonance. What does it do? Nothing. but induces a light shift. Then I'll bring another laser, which will be on resonance. And I will try to induce a transition. The first one doesn't induce any transitions. If I look at the excited state population, I see nothing. Now I'll bring in another laser. So the first one is strong but off resonance. So it is strong enough to make a considerable light shift, but it's off resonant enough that it doesn't do anything. Doesn't move populations around considerably. The other one is on resonance and weak. And then I'll try to play with its frequency and ask, when? When will I excite population? When will I hit resonance? The answer will be not at this frequency, but actually at this one. So the frequency, the transition frequency changes. Now, this had a name in the past. The name was this effect. I had a name in the past, it was the AC Stark shift. But Stark, we don't like him. Definitely not today. Stark, well, he won the Nobel Prize for discovering the Stark effect. But he was I think the only real great scientist that was the German great scientist that really bought on, very invested deeply in Nazi ideology. He was the chief scientist of German science. He was like, okay, the two great German scientists before World War II, well, Einstein was there and many others, but most of those fled. Those who stayed were Heisenberg, well, Planck, but he was already old and didn't do much, and Stark. Heisenberg somehow played all fields. He stayed in Germany. He kind of worked on the German bomb, but he did try to help Jewish comrades, and maybe so he was trying to somehow run between the droplets. But Stark, no, he was. He believed. He was a true believer, and that means that you can be a really great scientist and a complete asshole. Professors today they don't mind their language.
Freedom of speech.
Yeah. So this effect is generally termed the. So that's the light shift. Okay. So we discussed that. And as I told you, this is a measurable effect. Let me tell you even a little bit more. If you remember, in the very first meeting, I mentioned Lamb and his paper about anti-photon. He doesn't like people using the term photon. Why? So first of all, now we can understand actually what the Lamb shift is. What Lamb understood. The point is that you see, the light shift is proportional to the intensity of the field. Now, what Lamb understood when he quantized the field, and we will do that in something like 2 meetings from now, that the vacuum intensity is what? It's the average field variation, right? So how much does the field extend from zero? And Lamb understood that this happens also for vacuum. The vacuum field is not zero field. It has some vacuum fluctuation of the field. There's a vacuum, and therefore this term exists even when the field is completely zero. From the fact that the quantum vacuum is not just zero, it contains fluctuations. You cannot make the field truly zero, and therefore this effect exists even when the field is completely out. And then the question, and that induces what is called the lamp shift. And then the question is, okay, so how could I measure it? How could I know that it is there?
Isn't it neglectable?
What?
Isn't it neglectable?
It's very small, but it's not negligible. You can calculate it, and you can show that the observed transitions of the hydrogen atom are not exactly where what, as always, what we taught you in undergrad physics was wrong. Everything we taught you was wrong, and everything I teach you is also wrong, because if you truly calculate the energies of the hydrogen atom, and if you measure exactly and you do an exact measurement, you will see that there is a shift. The lamp shift is there. It is indeed very small, but it is observable, and that's why Lamb got the Nobel Prize. And we will discuss the lamp shift later in the course. But now you can see where it comes from. The fact that when we quantize the field, then you can start to see things like that. Okay, so now we learned a lot from this. We understood that every time that we look at a different way, we learn something. We still need to solve a problem. The problem is, where is the steady state? This is oscillating forever. Will it? And the answer is, we started to talk about that last time, was, well, in a way, yes and never. Always and never. What do we mean? The question is always, do I know the Hamiltonian? Do I know it? The answer is, no, you don't. Or at least, if I had just one atom sitting quietly, specifically at some place, where there's no stray fields at all, there's no magnetic field from Earth, and there's no, I don't know, light from lamps around, everything is perfectly dark and quiet, and this atom is just sitting there, and I turn on a laser with a perfect frequency that never moves, then maybe, and I know perfectly the intensity of that laser at the atomic location, then maybe. So then, first of all, maybe I can say that I know these. And still, even in that case, there is something that I don't understand, and that is the spontaneous decay. The fact that an atom like that, if you put it in the excited state, it will not stay there forever. It has a lifetime, and it will eventually fall down. And different transitions have different lifetimes, but this is a fact that we cannot explain, at least not within this model. We expect this state with no field to be an eigenstate and stay there forever. Why does it decay? Again, because of the vacuum state. The vacuum fluctuations, the same ones that can generate the lamp shift when they are extremely far away from where highly detuned, they can also induce a transition. And that's an explanation for the spontaneous emission. But we're not talking about that yet. Right now we're talking about, within the classical part, we have no way to explain spontaneous emission. But forget that for a moment. Even before spontaneous emission occurs,
The point is that I don't know. What do I not know? Okay, first of all, I have many atoms, not just one. They're not all in the same conditions. Some are moving, some are not. Those that are moving have a Doppler shift. Those that are sitting locally don't. So the frequency, the detuning, depends on which atom. Is it the one that's running away? Or is it the one standing still? Another thing is that those atoms are sitting at different locations. So the field is not necessarily exactly the same. You could have, as you know, you can have a Zeeman effect. So if there are some spatially varying magnetic fields, then the different atoms will feel different fields and have different energies. The other thing is the different locations. I have a beam of laser. It's not exactly the same everywhere. So different atoms will have a different strength of field. So across the ensemble, and what I see is an average. I never really measure a single atom. Sometimes I can, but it's hard. Usually the experiments that we do are ensemble experiments, and then we have we have effects of, first of all, knowledge unknown. Okay, so I don't know the true detuning of every atom, and the different atoms have a different detuning because they are sitting at different locations and they have different Doppler shifts. And I don't know the strength of the field for each one because well, the laser may change. And another thing that happens is that this Hamiltonian does not represent the complete interaction because they also, for example, collide. If this is an ensemble, so there can be collisions. They can collide with the walls, they can collide with each other. A collision is a Hamiltonian part that I neglected. During a collision, the two atoms feel each other. There's an additional term in the Hamiltonian of each atom which relates to the fact, to the interaction energy between those two atoms. Now, during the collisions, therefore, their energy levels move. So that means that this time-independent Hamiltonian is only an approximation. The real Hamiltonian is maybe sometimes, most of the time, time-independent, but then there's a collision, and then during the collision, things are, I don't know, moving around. And then what happens? Of course, what? Well, you go back, but you acquired an unknown phase. You suddenly, and those oscillations are very critical on phase. So what will happen is then that the collision just causes an atom to lose its memory. It's no longer, the coherent oscillation is no longer like that. So for those reasons, the steady state will emerge. Now, I don't have a way to model these things completely because these are problems of me. I understand what could happen to the atom, but I have no way of actually following this. I don't have any control over collisions and when they happen. So I can only treat them in a statistical manner. And the same goes for the okay, so the same goes for the Doppler shift and other things. So we're going to say, look, we have an ensemble average. I want to find a way in order to treat that. And now, okay, yes. So now we're going to talk about, we want to talk about the Bloch sphere. Now,
Okay, so it's a Bloch sphere. Those are actually the optical Bloch equations. And we want to talk a little bit about the density matrix. Now, I want to say something. We constantly talk about the state. But the state, which is C ground, C excited in the case that we discuss here, the state is not something that we can measure. Those are two complex numbers. If you have an overall phase, there's nothing you can do in order to measure that. So I don't know this. What can I measure? I can measure things like, so this is not measurable. What can I measure? I can measure the population. Those are things I can measure. And I can measure also the relative phase between them. Okay? So the relative phase between them will be depend on something like that. Sorry, not 1 and 2. Round, etc. And to be honest, what I can measure is this averaged. I can measure those averaged over the ensemble. Those are actually measured quantities. Now, I want to think, so I want to define, so we can define the density matrix. The density matrix rho, which for a pure state, only for a pure state, is simply this. In a moment, we'll describe what it is in the general case. This is for a pure state. What is it? I'll remind you. Of course, you can calculate this CG star and CE star multiplied by CG CE. The other way around. I'm sorry. Of course. Yeah, CG CE here multiplied by CG star CE star, like that. And this is the matrix that looks like that. C ground, absolute value squared, C excited, absolute value squared, C ground, CE star, and C ground star, CE. So you can see that this matrix is related to the observables that I have. That's for, and then we can say, wait, and what happens? So this is assuming that, so if I know the state, I perfectly know what the state of the atom is, I can write that, and this is just a, I don't know, either a clever or stupid way to write the same information. And what happens if I don't know? What does it mean that I don't know? It means that I have, the quantum state of each atom, or in general. Now I can So, and in general, I can say that rho equals sum over all possible states, the probability of now, the density matrix is an extremely important tool in theoretical physics, and I'm going to do it a great misservice in the fact that I will not say anything about all the things that you could do with the density matrix and are very, very useful in theoretical physics. But there is something that we can say, and that is, how does that look? What is this? How does it change in time? And we know, I mean, of course, we know the Schrödinger equation, so we can ask something like, we know that I h bar psi dot equals this. So rho dot, what is that? Well, in the other case over there, it is this psi dot psi plus psi dot. So I can write that, of course. And note that this can be this, what I just wrote for a single state. If I just look for on the general case, it stays that way. So I can have here sum over n, Pn. This doesn't, assuming that the different, well, we should be careful a little bit. No, that's actually okay. I can write that, and I can just, basically what will happen is that we will find that rho dot is just simply this. 1 over I h bar. It's just the Heisenberg equation. I think up to a minus sign, but forget about it.
Very good. If you take I up, then if you take I upper
The denominator.
to the numerator, you can get the minus.
Okay. Good. So, okay. Now comes another point. And that is, well, I treat the density matrix as an operator. Now it is. Among operators, this can be considered an operator. This is the operator of projection on the state psi. So this, the density matrix is the projection operator, and we are looking at its dynamics. The point is that the Heisenberg equation actually has another term. This. Now, okay, so if you have
some operator that also in itself contains some time dependence, then this will be the Heisenberg equation for it. And it relates, by the way, to the Hamilton equation in classical physics. The Hamilton equation in classical physics, if you remember if you had a good teacher in analytical mechanics, if you were lucky enough, that have told you about commutation, the relation between commutation relation and Poisson brackets, then you could see that this would be a classical equation. Now there is an interesting thing. I added this, but look at this definition. There's no specific time dependence. So, okay, assuming everything is known, then this is actually 0. But the point is that I don't. This gives me a way to model the unknown parts of the Hamiltonian. So this is phenomenological. This is something that I introduce myself due to the phenomenological understanding of what is happening in my experiment. So this is
here you suggest that all the stuff you don't know are time dependence.
Well, in a way, yes, because they are averaged. On average, they're 0. Okay? Collisions, on average, Doppler shift is 0. It could be positive, it could be negative. On average, nothing happens. If there is a constant shift of something, then this is something, if I have a DC shift, then fine. I can measure the magnetic field in the lab, and I can recalibrate my experiment because I can include the Zeeman shift that is there inside, or I can kill it by some offset. The problem is always with the time-dependent stuff. That that they're not staying, and I don't know them, so I cannot compensate for them. So this is a phenomenological thing that we will induce by hand to account for decays. Account for decay, decoherence, and so on. So now, okay. So I'll look for, okay, so we can write so I'll look at the density matrix rho, and this is rho 1 1, rho 2 2, rho 1 2, and rho 2 1. But rho 1 2 1 is just rho 1 2 0, and these are, this one is basically C ground absolute value squared. This one is C excited absolute value squared, and this one is well, okay. Here we should be careful. So there is C ground, C excited star, and of course everything is on average.
Wrote the difference.
What?
You wrote the opposite down there.
Doesn't matter. You want it like that?
No,
Fine.
you said you need to be careful.
What?
You said you need to be careful.
Yeah. Now, so now we can write just, okay, so I can use this. I have the Hamiltonian over there. I can calculate. Now believe me. Okay, so now so I can write the equations for
Okay. So I can write rho 1 1 dot and rho 2 2 dot and rho 1 2 dot. I can write also rho 2 1 dot, but there's no really a point in doing that in a moment. And then what we get is this: I omega naught times e to the I omega laser t plus e to the minus I omega laser t divided by 2 times what? Rho 2 1 minus rho 1 2. Now this is simply the imaginary part of rho 2 1 or 1 2, because this equals that one conjugate. And then here the same thing times with a minus sign. The only difference is everything is the same. The only difference is that we have a minus sign in the beginning. And then if we look at rho 1 2, then we have here omega atom rho 1 2, and then minus I Rabbi times the same thing, this times what? Times rho 2 2 minus rho 1 1.
Omega atom is with an H bar because it's outside.
No,
H
bars. All H bars are gone.
But the omega not include the divide by
This?
H bar. Yeah.
So this one, yeah, H bar
So
is there.
the omega atom at the beginning should have an H bar, no?
No, omega 0 is defined as these.
It's the units.
What?
So where's the H bar part of the first term?
There's no, well, if there should be one here, there should be one there as well, or in both of them there should not be one.
Okay.
What I mean is that you're right that this has the dimensions of energy.
Yeah.
And that's why I divide it by H bar to make a scale which is frequency. So the field is measured in frequency units because it is multiplied by the dipole and divided by H bar. So,
Okay.
and then here again, so this is minus I omega atom rho 2 1 minus I. Same. And again, so now you can see that, and again I can move to the rotating frame. Let's explain what moving to the rotating frame would mean here. So moving to the rotating frame, we just said, look, I look at C excited as being B excited times e to the minus I omega laser t. So that means that, and C ground is simply B ground. What does that mean? It means that C excited absolute value squared remains and B excited absolute value squared are the same. The only thing that changes due to that are the cross multiplications. So we can see that under this assumption, C ground, C excited star, that is B ground, B excited star, times e to the what? To the I omega laser t. So that means that this would be rho to 1, and this would be rho to 1 prime times e to the minus to the plus, times e to the I omega laser t. And of course, in the same way, rho 1, 2 equals, then I never, maybe I don't remember, but this equals rho 1, 2 prime e to the minus I omega laser t. So, and so I want to move to those. So I'm going to say, look, I'll choose rho prime, rho 1, 2 prime equals rho 1, 2 times e to the I omega laser t. That's what I want. Why do I want that? Because of course then this will almost disappear and I will have here only delta. You see how we've done that so many times. But if you don't see it, then ask. So when we do that, then instead of here by doing this, what will happen is that here instead of omega atom, I will have the detuning. There will be omega atom minus omega laser. That's one thing that will happen. The other thing that will happen, sorry, I'll do it a little bit slower. Okay, this remained omega atom. What will it do? Okay, so one thing that it will do is it will make this term almost disappear. The other thing that it will do is, again, here we will have a rotating term and a counter-rotating term. One of the terms will survive, we will throw one of them and keep the other. So doing this trick brings us choose this and throw the counter rotating terms or cathode ray tubes, you choose. Nobody knows what a cathode ray tube is anymore. But when we do that, we find the following four equations. Rho 1, 1 prime dot, but this is now, I'll put the primes for now, but equals half I omega 0 times, sorry, I'm not going to, I'll rho 2, 1 minus rho 1, 2. rho 2, 2. So equals the same thing with a minus sign. What did I write there? Okay, the same. Okay. And in general, I can say that rho 2, 1 is just rho 1, 2 star. It has to be. So I don't even need to continue writing it. And you can see that we have actually, okay, so we have 3 parameters here. What are the 3 parameters? I can think of them as being the excited state population, the ground state population, and the relative phase between them. This is the ground state population, this is the excited state population, and this, well, it contains the relative phase between them. Tells me what the relative phase between them. But I can also think of the parameters as being now, okay, so, and there would be, and there's the things that I didn't include, and that would be plus decay, right? This plus is where I will put decay, and because I will need to write beyond that, we'll get to that in a moment. We haven't done that yet. So right now we were looking only at the Hamiltonian part. So now, but I can say that there are 3 independent parameters. But in a way, they're not even 3, there's only 2. Why? Because the total population is constant. So like rho 1, 2, so I can say that something like I have the important parameters that I have are rho 2, 2 minus rho 1, 1, which is, this is population difference between the 2 states. I can talk about rho 2, 2 plus rho 1, 1, but this is just constantly 1 in most cases. We can talk about cases assuming that population doesn't disappear. There could be experiments, by the way, where population does decay, where the population is not constant. When could that happen? When the atoms can, you have two levels, but they both are not the ground states. None of them is the ground state. So population can decay out of there. That can be what we would call an open system, where the atoms can live within that range that I'm looking at, but they can also just decay to another state and disappear. Sometimes, for example, a background atom can hit an atom in my trap and kick it out. So it just disappeared, and that would be a situation where the population is not conserved. It could decay. But so I can talk about the parameters can be the population difference, population sum, which sometimes is a constant and sometimes not.
and the coherence between them. So, and basically we can see like, and the real part and the imaginary part of what? Of rho 2, 1. Or rho 1, 2, I don't care. So now I'll give those things a name. We will call that one W. I'll call this one U. And I'll call this one V. Just a name for now. And what about this one? I don't need it right now. I think about the fact that it is a constant. Is a constant in a closed system. The total population. So, I enjoy speaking, but and so now we can actually look, and look, you can see that all I have here is the imaginary part. So if I look at the dynamics, what induces the dynamics, why did I choose those? Because those are the things that induce the dynamics. So here we have, this is V, this is again V, and here we have W. Okay? So now I can write the equations. So under this definition, you can see that I can write W dot. W dot is the difference between those two. So it's the difference between those two. So it's just simply, and this I will go with the V. So all I will have here is omega 0 V. With a plus or a minus, depends on your choice. Then I can write what is U dot. That's also easy, because you can see it from here and you will identify that it is simply delta V, and V dot is delta U, just to make sure, minus delta U minus omega 0 W. New equations. Okay, those are the Bloch equations, and I do want to give you some time off, because I think that maybe you got a little bit tired. Let me just say something about those. Those equations, well, they don't look clear, but I can, if I look at this vector, if I think about U, V, W as a vector sigma, it's a vector in some fictitious state, in some fictitious space, then this equation is extremely simple, because this equation becomes sigma dot equals some Rabi vector cross I'll show you in a moment. Now, this is something, this is very convenient. Why? Because this is what Sevivon, the spinning top, does. It nutates. This is nutation. I'll show you in a moment how it comes. But what's nice about it is that now we can understand things in space. I'll tell you, things will start moving. Like, what does the spinning top does? Well, if it stands like this and the gravitational field is down, then it will just nutate around the field. This is what it will do. We know it already. So those are things that will be easy to think about. Okay? We'll describe that in a moment. But let's take a break. 10 minutes to breathe and go to the Jabutin if you need. So, are we missing some people? What?
נראה שכן.
Hmm?
נראה שכן.
כן, כן.
יכול להסביר בקצרה אולי איך מגיעים ל-RO IJ? קצת...
או איזה?
כאילו ה-RO.IJ. כל הנגזרת הזמנית של האיברים במטריצת הצפיפות.
לאלו?
כן.
מאיפה הגיעה המשוואה הזאת?
כן.
תראה.
הנגזרת של המטריצת הצפיפות אני מבין.
זה כל מה שיש שם. אז אני מסתכל על כל אחד מהאיברים שלה.
כאילו איך אתה שרת בין, כאילו איך אני מבצע את החישוב של הממוצע על המקדמים של, נגיד רואה אחד.
בינתיים בוא נבין הממוצע הוא עובר כלינארי דרך הדבר הזה. כלומר, כאשר אני אומר בעצם קודם כל לגבי הסטייט, הראש של הסטייט הטהור, את זה אתה מבין.
כן, כן, נכון, זה הגדרה.
אז איך גוזרים אותו? הכל ברור. אז עכשיו אני בא ואומר, בסדר, ומהו רו האמיתי? הוא סכום על NPN פסאי N. אתה רואה שבעצם זה סכום על N PN, בוא נקרא לזה רו N. אז עכשיו אם אני מסתכל על הדוט של זה, זה בסך הכל סכום על הדוט של זה. ולכן כל אחד מהם, רו IJ, דוט, הכללי, הוא סכום על NPN, רו ה-N'i, סליחה, כן, הדוט, IJ. כלומר, פשוט הממוצע המיצוע נשאר בחוץ, כל הזמן. אוקיי. Sorry, we'll be back in English. So going back to here, let me explain this a little bit further. So what we see here is that we have we just wrote those equations, and that's nice. So if I look at U dot, V dot, W dot, that equals what? That equals, I can write like an equation which says something like yeah, okay. So for U there's 0, delta 0. For V there's delta 0 minus omega 0. For W there is 0 And as we said, we can verify just quickly that I can think of this as being a vector sigma dot, which is the result of some vector omega cross the original sigma. And this vector omega, this omega vector, is what? It is omega 0, 0 detuning. Detuning minus detuning, I think. Yeah. So this is the this would be like an angular momentum, and this would be like the gravitational fields. In our case, it's a fictitious angular momentum in a fictitious gravitational field, but the equation is the same. Within this fictitious space, the dynamics is extremely simple. By the way, so why are those called the optical Bloch equations? Well, because Bloch discussed a magnetic spin in a magnetic field. Magnetic spin in a magnetic field does exactly that. It does real nutation in the real space. The spin of the spin has a direction. And if there is a magnetic field in space, it will nutate around it just like a spinning top mutates around the gravitational field. So exactly this. And then, so those are the optical Bloch equations. Why? Because the dynamics is simply the same, but it now happens in a different space. It's not in real space, it's in some fictitious space, where the coordinates are the population inversion and the real and imaginary part of the coherence. And now we can understand things like, okay, so we can analyze cases. So now we can think about simple cases. Psi at t equals 0, the state is in the ground state, all population is in the ground state. So that means what? So W equals what? W is population of excited minus population of the ground. The excited population is 0, the ground population is 1, so that is minus 1. And then U and V are 0. Okay. So that means that the state vector points down. So this is the state vector sigma. Now we assume that the field is on resonance. That means delta equals 0. So the field vector is simply omega 0, but in the x direction. So that would be omega, the vector omega. And then, so now we need directions in space. So we have, that would be the Z direction, that would be the X direction, that would be the Y direction. And here, of course, we have, well, you know. And then what will it do? It will rotate, and it will make complete, it will rotate around the field, and because it's at 90 degrees, they will keep the relative angle between them, and it will do a rotation. It will nutate around, and it will make a complete rotation. So after what? After a time that is dictated by this, it will be here. So now we can understand what happens is that we are rotating around the field. Okay? So if the field is this way and my state is that way, so after half a cycle I'm completely up. Full population inversion. And then after another half a cycle I'm back down. And I can continue this. If I am off resonance, what will happen? If I'm off resonance, then this state has also is no longer at X. First of all, it becomes longer, and the other thing is it is not at
It won't go between -1 and 1, it goes through smaller.
Correct. Let's think of completely very highly detuned. Highly detuned means that this is much larger than that. So that means that I originally was in the ground state. And where is the field pointing? Almost the same. Okay? If I am exactly the same, then okay, nothing happens. I'm just sitting down there. But if there is a small angle, then I'm making some nutation around that. It will be faster because the overall length of that vector is larger, but it will not go all the way up, it will be just rotating around. So now I can immediately tell you about something that there was no simple way to understand before, but very easy to understand now. And that is adiabatic rapid passage. Okay? I'll explain in a moment. So we just realized that there is a way to transfer all population from the ground to the excited state. We'll do Rabi oscillations, Rabi flops, like that. Meaning, we'll put the field exactly on resonance and wait half a cycle. But let me tell you, this doesn't work very well in an ensemble. Why? Because there is a detuning for some atoms, but there's no detuning for others. So some atoms succeed, others do not. Some atoms sit where the intensity is slightly larger, some atoms sit where the intensity is slightly less. Then some of them are moving fast and maybe going beyond maximum, and some of them are moving slow and didn't reach there at all. So the success with the Rabi pulse to transfer all the population up is not imperfect, at least in an example, because I don't know exactly that I hit the exact Rabi condition. But let me show you another trick, surprising, and that is I'll be highly detuned on purpose. What happens when I'm highly detuned? Well, I'm mutating down there, like that. And now, let me slowly change the detuning. Okay? What happens now? I'm mutating around the field. And now I'm slowly changing the detuning. So that means that I'm taking the field that was initially pointing down, and then I'm slowly moving it. Less detuning, less detuning, less detuning, it becomes like that. And then more detuning, more detuning, more detuning, more detuning, but to the other side, the opposite side of detuning, and it will become like this.
You keep the small notation around the state, but you take it all the way with you.
Sure.
Yeah.
And this would be, so that is adiabatically changing. What happens? So I am mutating here around that field, that is, nothing is happening, And then but slowly I'm changing the field, so I'll follow it, adiabatic rapid following, and I'll end up here. And this will be for everyone. Because what is the difference between the different atoms? Well, they have a slightly different detuning. Well, I don't care because I started from a huge detuning and ended in a huge detuning. All of them started, so I was way off. I was much more. This is something that most good engineers know. If you are fighting against an unknown parasitic capacitance somewhere, then the best thing to do is add a much larger capacitance that you yourself control, and then you know what is happening. You're not in the hands of some unknown parasitic effect, but you control the situation. So if I don't know the detuning of all atoms, let's make the detuning huge. So for all of them we have a huge detuning. And if some of them are rotating fast and the others are rotating slow, I don't care either. All they're doing is they're mutating around that field vector. And what will happen? They will all mutate, some faster, some slower, around that field, and they will all end up excited. So a adiabatic rapid passage is much more effective, much more robust to what we would call inhomogeneous conditions in the atomic ensemble. Inhomogeneous meaning not all atoms feel the same field, not all atoms feel the same, have the same detuning. I don't care.
How you get this?
What?
How do you do this? Taking it from.
That's very simple. I mean, what you need to do is tune the frequency of your laser. Have it below resonance, and then we say a adiabatic rapid passage, which means, so that sounds like a contradiction. A adiabatic should be slow,
and it's rapid.
but it's still okay. But you still want it to happen faster than the decay, than the spontaneous decay that could happen, and therefore you cannot make it as slow as you want. But it can be sufficiently slow and sufficiently fast at the same time. But then what you need to do is just sweep the frequency of the laser, and then between what and what. And the point is, okay, so let's give numbers. For example, for a rubidium atom, the transition between the ground and the first excited state is at about 780 nanometers. 780 nanometers, you can calculate what is the frequency. It's about 13, it's about 400 terahertz. Now the point is, what is the width of the transition? Okay, the width of the transition is about, including Doppler, is about half a gigahertz. So that's 6 orders of magnitude down. So we can have a detuning of, say, 5 gigahertz. That's already quite a large detuning. It won't excite the laser. You need to hit exactly within half a gigahertz to make excitation. So you start with a detuning of 5 or 10 gigahertz, that's pretty large. And then you change very quickly, sweep that detuning from 10 gigahertz below the resonance to 10 gigahertz above the resonance. You can do that electronically by adding some phase shifter to your laser, and this will bring everybody up. So we've understood, we've thought about like these are Rabi flops or rotations, and we talked about a adiabatic rapid passage. And that was, yeah, okay, so we were saying something like, so that, sorry, That is the vector sigma, and that is the vector omega, and all we're doing is nutating around this, and then we slowly sweep the vector delta with us. So on the way we are nutating around here, and finally we will be nutating around here. And so now I want to say something about, I would like to say something about Ramsey. Fringes and Ramsey method. We'll discuss Ramsey in a moment. I'll tell you for a moment what Ramsey is, okay? That is, what happens if I turn off the field? I make the field be 0, okay? So let's assume I'm perfectly on resonance, okay? I start okay. If I'm perfectly on resonance, the field is going that way. So I'm starting I'm moving. Oh, somebody turned off the field. What happens? We stop. Things just don't move anymore. And potentially then I can turn on the light again and up, I'll continue. We'll discuss why should someone want to do that. It turns that this is a very good idea to do. Like make the swap, or not in just one shot, but in 2 shots, with some time in between. We'll understand in a moment why it makes sense and for what purpose. But before that, I want to the point is that the Bloch equations allow us in a very convenient way to include decay. Now, and here, and it's a phenomenological one. What do we know that happens? We know that there is spontaneous emission, right? That means that if we put all atoms in the excited state, W equals 1, all atoms are here. After some time, they will all decay back to the ground state. So W itself has a tendency to go to -1. It is being drawn to -1 by spontaneous emission. We don't know why, but we know that it happens, and it has some time. So if I want to add, to have the Bloch equations with decay and decoherence, then I would say, look, W, that happens, but I also know that there is this minus, let's see, W plus 1 divided by tau 1. That's the decay time. That's the population decay time. Now, I introduced it by hand. I don't know where it comes from. But it just happened, so I put it there. I want to describe what is happening without saying where did this come from. I just measure this time, and I'll introduce it phenomenologically. And then there's another part, and that is what happens to the coherence. Now, for example, so here
those two, they also decay. This is the decoherence time. Now, why do I say this? Let's remember that U plus IV is what? It's just rho to 1. Or in other words, this is C ground, C excited, star. And maybe the other way around, I don't care. Okay. Now, this is the one thing that contains the phase. Now, as we just said, sorry, I was in B, so let's keep it in the B basis. So this contains the phase relative, or the phase in the rotating frame, in the laser frame. So relative to the laser. And it rotates at the detuning, right? Now, the question is, and this is important. Now what happens, but now we are averaging this over the ensemble. So for example, let's think, what would happen if the different atoms have different detunings due to Doppler? So some of them are moving fast, some of them are not. And the Doppler shift at 300 Kelvin for atoms is about half a gigahertz, several hundred megahertz. So that means that some atoms see a detuning of 0, others see a detuning of 100, 200 megahertz plus or minus. So that means that some of them are acquiring, this phase is rotating fast. So then what will happen is that I will see that the average very quickly becomes 0, because some of them are, some of them have detuning 0, they just sit there. Others have a non-zero detuning, so they're, I don't know, somewhere else. And on average, this did somebody knock on the door? No. So therefore, that's why we call this, it's decoherence, because the atoms lose coherence. And in this case, we have to separate between two types of decoherence. The decoherence that I just told you about is each atom is perfect, nothing happened to it. But what happens is that the ensemble, on average, the effect disappeared. Why? Some atoms are at detuning 0, they sit here. Some atoms have some, I don't know, some other detuning, they currently sit there. Others sit here. On average, they are spread all over, and the average is 0. But each atom has a very well-defined U and V. It's just that the average over everyone is disappeared. Now, and then there's, so this is what I would call an inhomogeneous effect. Different atom classes, in this case of discussion that have different velocities, have different coherences. So that's, so we can write, so 1 over tau 2 has
I can say that it can have, let's call it, it's divided to 1 over tau 2 inhomogeneous due to the inhomogeneity. And then there's the homogeneous part. What is the homogeneous part? Well, let me give you an example. The atom is sitting there minding its own business, and then suddenly another atom comes, hits it, and interacts with it, shifts its energy levels. For a moment, it becomes highly detuned, and then comes back to being at 0 detuning, but the phase has gone where? Nobody knows. So that means that this one atom, this specific atom that was sitting nicely at 0 detuning, ended up where? I don't know. Anywhere around so this is an effect of memory loss. Suddenly the atom lost its memory. Collisions, so therefore collisions are considered a homogeneous effect. Why? It happens to all atoms. If I could microscopically follow each atom independently, then maybe I could, I could follow what is happening. But this is something that happens just from the fact all atoms experience this. There are no classes of atoms. I cannot divide the atoms into classes where I could say, look, I can look only at the atoms at 0 velocity. They're perfect. Okay? The others I'll forget about. Okay, I'll just pick those, and then I'll see that they're standing nicely like that. But even those get sometimes hit by somebody and they get knocked out. So even those, even if I could follow them, meaning I could forget about the decay that is due to the inhomogeneous behavior, even those would still decay eventually because some other things happen to them, and those are homogeneous. Those happen to all atoms of all classes in any way. Okay? So inhomogeneous things are things that go like different classes of atoms. That can be Doppler. That can be inhomogeneous field, field, magnetic or electric field across the sample. That could be, or inhomogeneous laser. All of those that make differences between atoms in different velocities or in different locations, all those are inhomogeneous effects. And they would cause the ensemble to average out very quickly, even though each atom has a very well-defined dynamics. And then there's the homogeneous part, and these are things that are homogeneous decay of all classes. And that would be, for example, pressure, which means collisions. And another thing is spontaneous emission. Also, this is something that also means if there was a spontaneous emission event, what happened? The atom, I don't know where it was before, it ended up down. So what happens to its U and V? Became 0. So that means, so having said that, it is clear that tau 2 is smaller. It cannot be, at maximum it can be equal to tau 1. Tau 1 is the population decay. what causes this? Primarily spontaneous emission.
So if it's
It's
only
very hard for a collision to be an inelastic collision that causes decay. Why? Because the energy separation between the ground and excited is huge. To get that from a collision is practically impossible. So a collision will not cause that. So even if you increase the pressure a lot, the population decay rate, it's going to be dictated by spontaneous emission. But the coherence decay rate will vary strongly. If you have a very dilute gas in a very homogeneous situation, you will have tau 2 equal tau 1. And if you are in a, I don't know, in a gas, in a dense gas with high pressure, maybe there's a buffer gas, I don't know, there are a lot of collisions, then tau 2 will be smaller. And we must notice that there is, usually people call this, and the question is, can we get rid of this effect? Okay. The answer is yes, we can. So let me explain something. Okay, so yeah. So let me tell you briefly about Ramzi. We'll talk about him more a little bit in the beginning of our next meeting. I don't know when that will be, but guys, you will tell me. So okay, so it's fine if we wait 2 weeks. If you tell me, Avi, we checked our exams and it's okay, we can meet next week, great. And then we'll have it next week. I'll let you guys choose. But staying with just a brief introduction to Ramzi. Ramzi said, look, if I want to transfer atoms from ground state to excited, I can do it with a single pulse. This is called a Rabi pulse, and it's called and it's also called a pi pulse. Why is that a pi pulse? Because a full rotation is 2 pi, and half a rotation is pi. Okay, so I can give a pi pulse or a Rabi pulse, and I can bring the population up. And the Rabbi say, no, you can do that in 2 stages. You know, we can go half pi, wait, and then do another half. For that, he got a Nobel Prize. Well, why is that worth a Nobel Prize? It's worth a Nobel Prize because when you stop the field, but you don't stop the detuning. I have a laser. Even though I stopped it, its phase is still running. And the atoms, I said, okay, I gave a pi over half pulse. Atoms are here, are they? Well, yes, if it was a short pulse and if it was a really quick pulse, then most of them got here. And now I turn off the field. Okay, I turn off the field, but the detuning is still there. The atoms are still running. So some of them are going this way. Some of them are going that way. And let's even for now think that all of them are the same. Okay? But so I'm trying to find the exact frequency of the atomic transition. Why? Because I want to build a clock. Okay? That was the point. Ramzi's trick made atomic clocks 10 times better. And if you can make atomic clocks 10 times better, you get a Nobel Prize. Okay? If you improve the precision of atomic clocks by a factor of 10, you get a Nobel Prize. Now, what does it mean? What does the clock do? The clock is, I don't know, But now I want to know that my frequency is correct. So I want to compare it to a very stable and non-moving frequency. What is that? That is the transition frequency of those atoms. So he has atom, and he wants to make sure, now I'm generating a frequency, I want to make sure that it is exactly the transition frequency for the atoms. So I want to make sure that my detuning is 0. Okay, I want to tune my laser such that my detuning will be 0. What can I do? Okay, I can shine the light on the atoms. And then I can and I can check if I'll transfer them. So I can try to give them a pi pulse and see if they ended up here. What's the problem with atoms? They don't sit tightly. They don't wait. What is the major? Those times, atoms were generated from an oven. So there was an oven that was generating hot atoms, and there was a beam. There was an atomic beam. So atoms were flying at 100 meters per second through some pipe. A pipe here. Eventually, they hit the wall. And in the middle, they had somewhere where they interacted with the atoms. So in a sense, they weren't really turning the field on and off. The field was there all the time. Why was it turning on and off? Because the atoms were flying through it. So the pulse was generated by the fact that the atoms are flying through. You have a region where you induce the field. It's not a laser, it's an Aleph field. So it's an Aleph frequency. And the atoms are passing through that region, and they get excited. And if you are at the right resonance, at the right frequency, you'll find that you excited all the atoms. But this is not very accurate. Why? Because the time of interaction is limited by the flight time. And you cannot make it very long, because the atoms they're moving. I cannot have a radio cavity that is this large. And then what Ramsey said, okay, you don't need to make that radio cavity so large, you just need to make 2 small cavities. One in the beginning of the pipe, and another one in the end of the pipe. And you shine your RF field on both of them. So what do the atoms see? They pass through one, so they get excited very quickly. And then what? They continue moving, and then they interact again. And now the question is, okay, but what was the detuning in between? If you are exactly on resonance, then what will happen? Then, okay, they left the field and they're running. They're running by themselves. They're running at what? At the detuning, but the detuning is 0, so nothing happens. Or it means that my laser is following the phase of the atoms as they are moving, and it will meet them here at the correct phase again. And then it will complete the transition and they'll go end up. But if they have some detuning, then on the way they will detune away, they will shift away.
You'll get lost.
Yeah. So you will get an effect of the delay between is not useless. It is good. It lets you see the dephasing that happens when there is a detuning. He understood that, and he analyzed this, and by doing that, atomic clocks improved tenfold, and Ramsey got a Nobel Prize. We'll discuss this in further details next time, because I think that yeah, maybe, I mean, you're all nice and you're already accustomed, but when lessons continue too long, I get bad reports, so and I don't want the bad report. So, questions? If you have any. Lots of them. What?
So today we're going to talk mainly about the Bloch sphere
a little bit about decoherence, but we'll go really deep into decoherence next tutorial.
תשמע, אם זה לא מוקלט נראה לי אתה יכול לא בעברית.
שוש! שוש נועם, שוש!
תשמע, כולנו מדברים פה עברית, הוא כאן. אני רציני.
But before we start, let me introduce you to our new classmate, the block sphere. Instead of drawing 1,000 bad spheres this tutorial, we're just going to use one bad sphere and then do a little bit of magic on it. So this will accompany us for the rest of the tutorial. So last exercise we saw that a two-level system can behave as a spin half magnetic field, and more specifically we can write the state at any given time as a vector. Why is it purple? What? Okay, I guess we're doing purple. It's fine. Yeah. C2E C1G, which is just a general representation, and we saw more specifically that we can write it using two angles, cosine divided by 2e plus e to the I 3 sine 3 divided by 2 ground state. We saw that every occupation state can be written like so, which the two angles correspond to an angle on a block sphere. So if I write some arbitrary state, I can also draw it on the block sphere, where the angle from the x, we do this angle from the z direction. This would be theta, which makes sense when we are looking at the vector representation, since the theta here represents the difference between the plus sign of the z and the minus sign of the z, which is the excited state or ground state. And phi, if we take projection of this vector on the xy plane, phi will be the angle compared to the x direction. So we can translate every state into a vector on the block sphere, which will be very useful for us very, very soon, and in general just an elegant representation, which is very, very cool. Alright, now following this mapping, we also defined last tutorial the Bloch vector, which is again just a different representation of this writing. We called it Q, or maybe gamma? No, not gamma. Sigma. That was the. I'm so bad at Greek letters. Which is the x component, y component, z component, and I don't remember if you saw it in the homework or not, or I did it in class. We saw that x, you can define it as u, which is equal to constant minus if you have any questions, just stop me. I'm just going over the reminder real quick. And of course we can do the same to the y. So let's call it to v. Minus I sigma plus minus sigma minus, which is the imaginary part of sigma conjugate C1, sigma z, value find the W, which would be which would just be C2 to the value square minus C1 value square, basically the difference of occupation. Simple as that. And using this Q vector, we also define a new way to represent the Hamiltonian. H equal divided by 2 omega vector dot sigma vector, where omega vector will be defined as omega 0, which is the Rabi frequency, cosinus stay consistent with what last time. Sinus field delta, which minus delta, which delta is the decoherence, basically the frequency difference between the laser that affects the system and the energy, and the frequency of the energy transfer between the two states. And now we'll see how we can use it and the Bloch sphere to make this entire complicated multi-page problem basically devolve into pointing at stuff. You will understand in a second. Okay, so first of all, I want to use this new Hamiltonian and try to explore the equation of motion. So I'm gonna erase everything, almost everything. So I have space. I'm not gonna touch my beautiful boy here. Alright, so using the Heisenberg equation, we can define the time evolution of the Bloch sphere vector. ddt I equal to 1 divided by I h bar phi h, right? And this will simply opening this vector up and using the commutation relation of phi with itself equal to 0, we can get 1 divided by 2i, commutation relation of phi j as sigma j, omega j plus phi k omega k. Right? Now I'm going to use the fact that you definitely found it your homework that you all did, obviously, that the commutation relation sigma I sigma j equals 2i epsilon ijk sigma k. Right? Will just mean, since those two will give us the same, sorry, let me just write it explicitly. This one will be so an ijk of sigma k omega j minus, note that I put a minus here because I had to switch the order of jk here in this commutator, so it will switch the order in this epsilon, minus sigma j omega k. Right? Now I'm sure I don't have to explain this very deeply, but this is just how a cross term is seen. So this is just so note this d dot t sigma vector will just be omega, let's just say omega cross sigma vector. It's also a vector, but we wrote the sigma without. Ah, actually, I did write a vector there, so I'm a liar. It's fine. Yeah. So this is. I'm pretty sure you saw this kind of time evolution somewhere in your class, but for everyone who learned the right-hand law, the right-hand rule, knows exactly what this equation of motion describes. Just a rotation on two axes. Before we go deeply how to use it, let me just say that this has a pretty simple way to solve this, which I'm not gonna do. But I will give you the final solution for this equation, which would be vector, which for convenience I'm going to define it as a column vector, not just for convenience. This would be divided by square. Good. Wait, wrong. Okay. T plus 0 squared there's no square here. Okay, just a bit long. This won't be in your homework, so it's. Oh wow. Okay, that's a problem. But we have time today, so I'm just gonna write it again. You know what, since it's not important for the next tutorial, I already failed at writing it once. It's in the tutorial notebook. We're not going to use this for the continuation of this tutorial, but it's a very useful formula. Just open it up, look it up. It's fine. Don't blame me. So now we'll talk about what this means. So, this means that we simply have to follow the right-hand rule to find out where our vector will go. So, if...
אפשר שאלה רגע?
Yes.
מה ההבדל בין Q גדול לסיגמה?
It's the same thing, just different name.
כי פה כאילו
סיגמה
אנחנו
וקטור
אומרים
Q
זה הממוצע שלו, לא?
It's the... What do you mean?
כאילו סיגמה וקטור זה הסיגמה X, סיגמה Y, סיגמה Z, אבל Q זה U, V ו-W. אז כאילו יש איזו טרנספורמציה ביניהם. לא?
I mean, usually when we... Both when I write on the board sigma vector and Q, it's the value, it's X, Y, Z value, like here on the sphere. I don't see a difference in the notebook, but let me just check again.
אוקיי, בסדר, זה לפי הגדרה. טוב.
Okay.
U זה לפי הגדרה הממוצע של X. נכון? ו-V זה של Y ו...
Yeah, I guess I should have been more clear when I said sigma vector. I don't mean operators. I mean like the vector of the values of sigma.
Okay.
Right. So let's see what happens here. Let's start with a simple example. If I have, this is also cool, this is fun. Do we have a red one? Yeah, okay. Purple will be the atom, red will be the laser, right? We have an atom, an ensemble of atoms, because we're cool like that. That goes straight down, to the direction of middle, and then I activate the laser in the y direction, which is out, the other direction. So what will happen? Well, vector down times vector forward goes to the right. So if this is the laser arm and this is the atom arm, the atom ensemble arm, we just do something like this. And I can do more because I'm human. Yes, okay. And now we can do some cool stuff with it. Alright, so I'm gonna transition to talk about in pi terms. When I say pi half rotation, that means I'm gonna do a quarter rotation around a circle. When I say pi rotation, I do full 180, so on and so forth. Obviously, it depends on the intensity of the laser times the time that you activate it, but I'm just gonna talk about in pi's because it's simpler, it's quicker. So, let's say I want to take my atom ensemble and move it to x positive, and then keep it there. What do I mean by keep it there? If I'm gonna just do this first step and do a half pi rotation, I'm gonna move my atom ensemble to the x plus state. But if I leave it there, it's just gonna start rotating freely because it gains phase, and we don't have some laser to change it. So what can I do to keep it at x plus always, all the time?
מתכוון שמסתובב וזה מסתובב סביב איפה?
It always rotates like so. The population would not change. The population ratio between plus and minus won't change, but the phase will change. Of course, we don't talk about spontaneous decay and stuff yet.
זה תכף מסתובב סביב ציר זה.
Yes. Yes, this is the ZX plane is just phase, so it will always do some rotation. But I want to keep it at plus. I don't want it to move. So one cool thing that we can do, since we know that this walk is a cross section, as a cross between these two, is say, all right, I move my atom to x plus, and then I'm gonna turn off the laser right here. Obviously, it's already turned off because I don't want it to go to Z plus. I'll turn it off and activate it again in the Z minus direction. And then I ensure that this cross will be 0, and there will be no rotation. This is called photon locking. This is the first thing. All right. Now let's go for something a little bit cooler, a bit more complex. Let's say that I do have some decay, and we know that if we have some spontaneous decay, we can't really just activate a laser put a red vector somewhere on the sphere and go to the Z plus direction. No single laser will do that. But what can I do to bring it up anyways? Well, let's think, I'm going back to the hands. Let's think I have atom ensemble on the minus direction, and then I put laser real close to it. What it will do, it will just rotate around it. I can't really do it, but you can imagine. Just rotate around it. Now what will happen if I move it, the laser a little bit, just a little bit, it will also still rotate around it. Now, if I'll keep moving it very slowly enough that I don't get my ensemble doesn't lag behind, it will slowly rotate around myself, and I can guide it, sort of guide it into whatever place I want on the block sphere. This is called the adiabatic passage. Let me write this name. What's this name? It's right here. I'm gonna take a laser very closely, and then my ensemble will rotate around it, and if I move the laser faster than the spontaneous decay in time scales, we're not doing that precise calculation for the adiabatic passage right now, but faster than the spontaneous decay, though we need to go slower than the rotation speed of the atom ensemble, I can basically force it, lock it, the ensemble itself, to my laser on the block sphere and move it to wherever I want, including a full population inversion. I think that's very cool. Alright. So this would be, these are the two main ways that we can play with it, two the main interesting ways. But what happens if there's noise? I mean, when you have a big when we want to do an experiment in the lab, we, for example, take a canister of gas, or we shoot atom through some cavity and then blast it with some laser. But atoms aren't nice. Not all of them are just gonna walk straight at exactly the speed that you want. So every one of them will just experience something a little bit different. They can hit and interact with each other and all that kind of stuff, which is very problematic. So this is why we need to explore a little bit the inhomogeneous broadening and inhomogeneous processes that can affect your ensemble. Yeah, all right. Just give us some room.
הקטע באדיאבטיק רק תתפס את זה שאני רוצה להזיז את הלייזר מספיק מהר כדי שהוא לא יצנח בחזרה לגראונד סטייט.
Which is...
ואז כולם תוקע אותו והוא לא יכול לרדת ואני יכול למלא אותו קצת למעלה.
Yes. Now think if you use a strong enough laser, this rotation would be very fast, and the time scale of this rotation will be much faster than the time scale of the spontaneous decay, and you can, like that, you can carry it to change it in the correct speed.
אבל אי אפשר להגיע להיפוך אוכלוסין בשתי מצבים.
Okay. In a perfect system, you can. Apparently.
Okay.
In a very weird way. Okay. So, let's do an example. Just, I threw out the inhomogeneous broadening and stuff like that. Let's do a little example, and as we go through it, you will understand the concept better, and you'll see one way, or maybe we'll have time to do two ways, maybe even three, how to fix it. Alright, so let's consider an ensemble of spin magnetic field, ensemble of atoms, of spins, in a magnetic field, constant magnetic field in the z direction. So let me just have some box, a lot of spin in it, a lot of particles in it, and we have some Bz. Bz is supposed to be constant, but making a constant field is very hard, so it has some probability in space to be it has some probability distribution in space. The form P Z equal 1 divided by square root of 2 pi delta BZ into the minus Fs squared divided by 2 delta Z squared, where delta BZ is much smaller BZ. Right? Yeah. So we'll start with the phi equal plus x in the space, which will give us some rotation speed around the x-axis, the z-axis, which will be equal to gamma of z. Well, gamma is just some geometric ratio between the field and the rotation. Right? Now the first thing we want to calculate is, let's write it in A. We want to calculate sigma x over time. It's a function of time. Okay, well, since we know the rotation, very simple to calculate it. We can just directly say sigma of x equals, this is just the time evolution from the Hamiltonian, z divided by 2 t times sigma z plus minus e to the minus I beta z divided by 2 t sigma z. Right. This is if you look at the last tutorial, this is the time evolution operator. Okay. And now I can open this phi x phi y in the xyz basis and find that and find that both of them interact differently with the computational relation regarding the sigma z up top, which will eventually give us 1 over 2 e to the I gamma beta z t sigma x plus I sigma y plus 1 over 2 sigma minus I gamma beta z t sigma x plus I sigma y. And remember that this is done in the Heisenberg representation, so this averages also in the Heisenberg representation, which means that we'll start in the plus x location. So both of this one, the y cancels out and the phi x will be 1. So we'll just simply get cosine gamma beta zt, right? Now, since we have the probability written out already, right here, we can take it and add it to our equation in the following way: x of t equal over integration of all probability in beta z of, let's give it a 1 here just so we can differentiate it, times p of z, which is the same as to say as p of gamma beta z but I'm just going to take gamma beta z to be omega for simplicity. Z d omega z or equal. This will just be, for lack of space, I'm going to jump one step, just opening the integral. It's going to be the real of 1 over 2 root of 2 pi delta omega z value squared, integration from minus infinity to infinity, e to the I omega z t e to the minus omega z minus omega 0 squared divided by 2 delta sigma omega z squared, yes, d omega z, which is simply just the real part of the Fourier transform here. So here this is all the math for this tutorial, so don't worry about it. Don't worry about it. This will be the real part of the Fourier transform, which is equal e minus square divided by 2 by square root of 2 pi divided by sigma z squared cosine sigma 0. Right? You'll see that because we have an inconsistent field, we'll get that the population, this one is sigma z, sigma x, this one is time, we'll do some cosinus, we see cosine pattern times some decaying Gaussian. So this inhomogeneity doesn't just rotate, just can interfere with the rotation, but this time we actually saw it just interfere with the population itself. All right, next part of the question. Okay. Next part of the question is they ask us what is the characteristic decay time? V well, we can very simply see from this equation right here that T2 P62 will be equal to 1 divided by delta z. How much your field is inhomogeneous, that's how fast it will destroy itself. Destroy the way. Alright, now see, that's the more important question. If the spin, let's write it, if the spin starts at plus in the z direction, describe how to do by half rotation despite right? So how can we do this? Anyone has any idea? There's a simple answer and then there's a cool answer. There are actually two answers for this question. Anyone want to guess? Well, well, the simple answer is basically saying, okay, we want to do a pi half spin. We just do it faster than t2, very, very fast. So we basically say pi divided by 2 omega y would be much smaller than t2 star, which means that we need omega y bigger than pi divided by 2 t2 star. Right. Just have a strong enough laser. Very, very creative. Right? And the second answer we'll do right now, but we're going to try a little bit of a different format. So I'm just going to erase everything, and then you can try to apply it to this problem yourself. What's the time? All right, we'll finish. All right. The next part is called spin echo. Right? Even though inhomogeneous broadening is an irreversible process by itself, basically describing a lot of different parts of the system evolving at different rates, and then eventually all those rates will diverge from each other and create an average of 0. You might have specific atoms, specific phases, but all of the phases together will be 0 on average. We can do a little trick to combat it. So, if I'm gonna quickly describe what we saw in the last question using our beautiful class pet here, you might think it's a bad circle. It's one of my best so far, so I'm very proud at least. So yeah. We started at, where's my red? Thank you. We started at x plus, and we had a laser going in the z direction. But what happened is that our system was not perfect. So let's say we have a few atoms, one of them after like a second moved here, one of them stayed in place. He decided he doesn't want to see the laser. One of them moved a little bit to the left, and so on and so forth. One of them here, one of them here. Right? Now, what will happen if I take my laser and move it to the y direction? In a very strong way, very fast. Now, we have our open decorated state over here. We flip it to the other direction. And then we return the Z processing or whatever there is that causes them to rotate in the X direction. Now all of our atoms, all of our spins or whatever it is you're looking at will just be sort of mirrored here. But the inhomogeneous sort of expansion in the X distribution will be the same. That means that this one that went, if we're looking from above, clockwise, will still go clockwise. So this one will go the other direction. And then, given the approximately the same amount of time on this side, we'll give it the same amount on the other side, that will close back up into a single file. This is called a spin echo, and the steps are pretty simple.
אתה אומר אם ניתן לו זמן אז חלק הם יתחילו לזוז לצדדים ואז אני אעביר אותם לצד השני בגלל שזה הפוך אז ניתן את אותה זמן והם יחזרו למקו בהתחלה?
Yep. Usually describing processes, we describe them starting from minus, so you do no laser. This is the start of the experiment. Then you do a pi half in the y direction to put them on the x, and then you give them some time to evolve, tau, which is then we want to check, and then we do a pi rotation in the y direction, and we give them another tau, and then we measure. Okay. Now there's a third option which you will explore in your homework, which is called Rabi spectroscopy. And I really debated whether I should go into it in the tutorial, because most of the work will be in the homework anyway. In the tutorial I'm just going to explain it hand wavy, which you will do no good for anyone. So I think I'll just keep it, I'll leave it to the homework. So we're done. We're done for today. Go over by yourself over the Rabi frequency section, Rabi spectroscopy in the tutorial notebook.
זה לא שלך אבל אין את זה אצלך.
In my notes there is none, because I moved all of it to the homework of the Rabi spectroscopy because I didn't like what was reading in the tutorial. But it's a good, but you don't actually need it to solve the question. It basically says that we can use this sort of process, the interferometry tool, which basically all of it says in the tutorial notebook. So there's not really much to go deep into it. So, okay, I'm also going to say that the tutorial notebook with some historical and useful and uses for this method, spectroscopy method, so that's why it's interesting to read about it, but not for me to explain about it because it's too much. So, yeah, there's already homework up, 2 weeks, do your homework. Good luck. The next tutorial we're going to go a bit deeper into spectroscopy and stuff like that, so...
זה עוד שבועיים, שבוע.
טוב, אני רץ לאותו ונתראה. ביום חמישי.
אתה מגיע מחר סער, נכון?
ביום חמישי.
כן.
כן, אני עובד...
מה יש מחר?
אני לא נמצא.
ביי סער.
ביי, תודה.
לא.